General relativity, step by step. Okay, so I've got this expression for the Riemann Christoffel tensor with 4 downstairs indices, and we've already achieved quite a lot of simplification because these cross terms here have disappeared in the wash. Right, so I've got left this thing here, and so what I'm going to do is I'm going to expand that. We know what the Christoffel symbols are, times di mu. Oh, we've got a factor of a half to deal with. What's the Christoffel symbol? Well, it's in this notation, it's di g, no, it's di something g do do plus di something g d d minus di something else g do do. And I'll do the other term in a minute. What have I got left? I've got I've got di mu there. I've got a g in the uppercase. I've got a gamma, which is this gamma here, and I've got a pi there. What I did was wrote down the other Christoffel symbol with 3 downstairs indices. So where does the pi go? The pi goes in the first place, it goes in the second place, it goes in the differential. What have I got left? I've got a beta and a nu. It's a beta and a nu and a beta, and a beta and a nu together. That's nice. Di mu is that di mu. We've got an upstairs index pi, which is summed with that pi, that pi, that pi, so we're in control. Minus di nu g, it's still a gamma, it's still a pi, although it's a different pi. It's summed here, it could be any letter here. Di something g d d plus di do g d d minus di blee g d do. And I've probably got to close lots of brackets. Yeah, I'll close that bracket there. Right, what's going on? We've got a gamma and a pi. The pi sums in the first place, the pi sums in the second place in the differential. We've got, what have we got left? We've got a beta and a mu. We're going to put beta and a mu and a beta, and the term with the different sign has got the mu and the beta together. So that's right, isn't it? Right. Now I'm going to remind ourselves that g alpha beta equals eta alpha beta plus h alpha beta. So that's constant and that's small. So what that means is, well, the differential of a constant plus something small, plus something variable, I can replace these g's with h's. And I can also replace these g's here with etas. Well, let me do it one step at a time. One step at a time. Equals a half g alpha gamma times, open brackets, di mu g gamma pi of di beta, I'm just copying from here, and that's an h pi nu plus di nu h beta pi, because all I'm doing is subtracting a constant, minus di pi h beta nu, close once, minus di nu from here, g gamma pi, and then I'll write the second term, di beta h pi mu, plus di mu g beta pi, copying from here, minus di pi g, oh no, it's an h. Ha. I'm doing it one step at a time and I'm still getting it wrong. H, it's this term here, mu beta. And now I observe that these terms here, these h terms, these differential of h's, they're small. So that means that I can ignore departures from flat space metric because they're of order. Oh, let me rephrase that. Let's just have a look at the first term. We've got g gamma pi times something small. Times something small. That's just the first term there. Equals eta plus h times small. And that means that I can ignore that term there. And that means that I can replace this g here with an eta, which is quite nice. I'll get rid of that. Just replace it with an eta. So it's a half. Oops. It's onto my pen. Oh, there we go. It's a half eta alpha gamma times di mu eta gamma pi times these terms here, di beta h pi nu plus this one, di nu h beta pi minus di pi h beta nu. Sorry, my pen is misbehaving here. Di pi h beta nu minus di nu. Oh no, it's not a g anymore. I can replace that g with another eta gamma pi. That's quite nice. You see, it's going to factorize, and we'll use the fact that it's an eta rather than a g later. Di beta h pi mu, copying from here, plus di mu, copying from here, h beta pi minus di pi h mu beta. Close again there. Right, now we make the observation that because this is constant, it commutes past the differential. I can take this term here, and because it's constant, it just moves here. And now I can use the fact, this is really clever, I can use the fact, if I imagine just moving that there, we've got eta alpha gamma, that's that term there, times eta, and then up here we've got gamma pi, and of course it's summed on the gamma. So that total thing equals delta alpha pi. That's quite nice, isn't it? So let's just do that. We've got a half of delta, and of course I'm going to use the features of this later, delta pi upstairs, alpha downstairs, di mu, acting on all these terms here, di beta h pi nu, plus di nu, copying from here, h beta pi, minus di pi h beta nu, minus. It's the same thing. Wait a minute, my pen's misbehaving. Oh, for goodness sake. Just a minute. Sorry, a little bit of a glitch there. My pen was misbehaving, so I had to replace the batteries. Where was I up to? We are contracting that. We're applying this identity here to that term there. Okay, so it's a delta. Look, batteries made it right thicker. Minus delta alpha pi. Of course, it must be the same thing. And we've got a di nu, and I'm just going to copy these guys here. Di beta h pi mu. Oh, for goodness sake! I think this pen is not behaving itself. Mu plus di, this term here, mu h beta pi minus, oh my goodness, h beta pi minus di pi, and then this term is h mu, mu beta. It's looking a bit rocky, but anyway. Sorry, another glitch there. I'm going to transfer pens. I see this one's a bit finer. Okay, where was I up to? I'll see if I can get rid of this. That's beta nu. There we go. It's kind of legible, isn't it? But it's a bit messy. Beta pi, I guess. Okay, so what am I going to do now? I've got a half. I can just replace. I can take this term out here. What delta does is pick out just the term where alpha equals pi. So alpha equals pi. So I may as well just not bother with the pi and just write alpha. So I've got di mu from this term here, di beta from that term there, h alpha nu, because the pi has turned into an alpha, plus di nu h beta alpha, because the pi's turned into an alpha, minus di mu di alpha h beta nu. That's nice, isn't it? Minus di nu di beta, that's this term times this term, h, and it's the same trick, alpha mu, plus di nu di mu h beta alpha, minus di nu, why is it di nu? It's because of that one there, di alpha, because the pi's turned into an alpha, h beta nu. Whew! There we go. Equals what? Equals a half. Now, I bet something's going to cancel, and I'm going to have to spot it here. Have I got my signs wrong? Yes. I was going to observe that these two terms here cancel, but I've got my signs wrong. That's a minus, that's a minus, and that's a plus. Here we go. So what cancels out? Now let me have my red pen here. And it's the middle term here that cancels out mu, nu. That's a mu and a nu and a nu and a mu. Yes, that term and that term cancel out. Signs are opposite, and all I've done is differentiate it in the other order, and we're using regularity conditions here. So I can go back to black. And what have I got? I've got the fact that it is a half di mu di beta h alpha nu, which is this term here, minus di mu di alpha h beta nu. It doesn't cancel out, does it? Nope, that term there. Minus this term here, di nu di beta h alpha mu. Is it a plus or a minus? That minus that, minus that, plus di nu di alpha h beta nu. And this whole thing is equal to r alpha beta mu nu to first order. There we are. Now, it looks quite bad. There's second differentials in there, but there's only 4 terms. They're relatively benign to work out, relatively easy to work out. And I just want you to appreciate how much simpler than the original form it is. It's much, much, much simpler. Here you've got a metric tensor outside the bracket, and you've got a differential of Christoffel terms, which is hard enough as it is. We've replaced that with a straightforward second derivative. And also the full version of the Riemann Christoffel curvature tensor has got these cross terms here, these product terms here, which we can just ignore in this approximation. So I'm going to stop there. I think that's beautiful. It's 12 minutes.